Are there any questions?
Yeah, how do you put your answer like for number 3 and 4 on the last lab report in rectangle form? I know, like we've probably gone over, I know we've done it a lot, but I'm trying to, cause I was following the video and I've got my like 2 answers for the one at the negative and positive field, but I don't know how I'm.
All right, so got the plus sign there and the minus sign there, this lab, right?
Yeah.
So if you establish a coordinate system with a I hat, j hat, and I guess you're finding the electric field from here and the electric field from there.
Yep.
And then you have the sum.
Yep. Yep.
I guess rectangular form.
But on 3 and 4, it wants to know what the ideal electric field is for the negative one and then for the positive, and it wants it in rectangular form. So.
Yeah, rectangular form. So if this is my coordinate system here, this is pointing in the negative I hat, negative j hat direction. Or if it's over here, it would be negative I hat, positive j hat.
Yes.
So if this is this 3 and 4, you found 53 degrees. So if you found it in polar form, this would be 5, I guess, meters per Coulomb. 233 degrees. That's polar form.
Okay.
You got the magnitude of it and then the direction based upon 0 degrees being here, so that angle right there. Rectangular form would be, given that convention, negative 3 newtons per Coulomb I hat minus 4 newtons per Coulomb j hat. All right. I wasn't sure whether your question was what did I mean by rectangular form, or how do you get from here to here?
Yeah, it's going from there to there.
Okay. The simplest is if I have the angle like this. So in the 360 degree form, then this right here is going to be, sure I did that right. The magnitude there times the cosine of 233 degrees I hat plus the magnitude times the sine of 233 degrees j hat. And then you use the calculator to figure that out. If you have it in the 360 degree type notation, not just the base angle, but that notation right there, the minus signs will come out of it. That minus sign will pop out when you do this. That's probably the simplest if you have it in that form. And it sounded like, based upon nods and various sounds you made, that this is not a problem getting it to here.
Yeah, I don't think,
Is
I
that,
think that's right. Yeah, I think I got it right. I just I don't know if I've got all the angles yet for the degree, like for the 233.
yeah, well, at least for point M, defining
You
that
use
angle is
that-
relatively simple because
you can use the protractor, can't you?
you can use the protractor or you can just count out squares
Yeah.
and do a ratio in arctan.
Yeah, I did a protractor, so I
Okay.
think I have it.
Brooke said that she would be running late today.
Okay.
Found a straggler on the way in.
I thought I had like 15 more minutes. I would have been very late, so I'm sorry.
Yeah, time.
Yeah.
It's
We'll eventually
relative.
get to the point where we learn it's relative. The faster you run, the slower your time is. All right. Follow-up questions on this? Other questions? All right. pick up where we left off. We're sort of recapping, just so I don't forget the recap. All right, so we have a set of equations when dealing with capacitors. We have the one that works for all capacitors, that the capacitance divided by the charge divided is equal to the charge divided by the potential difference between the two plates. And again, for a capacitor, all you need is two conducting planes which will hold a charge and then some gap in between them. And then when you hook it up to a power supply, you get a charge and the negative of that charge on individual plates. Now traditionally, I usually have the positive plate on the left-hand side and the negative plate on the right-hand side, but it doesn't have to be. Well, depends on how you stick the battery in. If it is truly a parallel plate capacitor, then we have another formula for capacitance, which is kappa epsilon sub naught, the area of the plates divided by the distance between them. That distance there is d. Kappa being the dielectric constant. And if this is a typical 152 group, despite what at least one of you will come up with, kappa should never be less than 1. This is one where, this is the lab primarily where XL, if you use XL to make the graph, when you do the slope, for whatever reason, it likes rounding off. And this is the lab where you can get an answer less than 1 or greater than 1, depending upon the rounding. I know that if the electric field is constant, which we are pretending it is between here, so if the electric field is constant, with respect to position, I mean, it can change with time, but if the electric field between the plates is the same, then I know that the potential difference between the plates is negative of the electric field dot product with the displacement. So if I'm going from the positive to the negative plate in the direction of the electric field, I'll have a negative potential difference, which makes sense because I'm going from the positive to negative. I'm going from a high potential to a low potential, so the change would be negative. And I know from when we applied Gauss's law that the electric field from the plates is equal to sigma over epsilon dot, or the total electric field is sigma over epsilon. The difference being the dielectric constant. Epsilon sub naught assumes there's nothing in between the plates. Epsilon assumes that you've got something between the plates. And so we can look at that relationship. Epsilon is equal to kappa epsilon sub naught. So, as we're looking at a parallel plate capacitor, there's basically 5 quantities that we can manipulate. There's capacitance itself. There is the change in electric potential, or the difference in electric potential, or the voltage between the plates. There is the electric field because of the plates. There is the total electric field, and the charge that's on the plates. These are the primary electrical aspects of the parallel plate capacitor. And then within the capacitor itself, we have 2 other variables that we can manipulate, or we have a couple others, physical properties, such as the dielectric, so I guess kappa, the area of the plates, the distance between the plates. Which are all just physical properties of the capacitor. I'll make 2 meters. So, oh, yes, Anna.
Quick question. So you said those top 5 were electrical, properties of a parallel plate capacitor, and the bottom 3 were physical properties?
Yes. In that, if I'm if I'm building a capacitor, these are the 3 things that I'm manipulating in order to affect those. Any of the component stuff, basically from the capacitor stuff on through chapter 21, it's all about how do you control the flow of current. Which, before I started saying that, felt like it was far more in sync with your question than it sounded after I said it, but.
It's all connected.
Yep, there you go. Other questions before we start trying to figure out what the 5 electrical quantities are for this particular capacitor? All right. So let's start out with what's the capacitance? Just to give you some sense, I'm just under 2 meters tall. So 2 meter by 2 meter plate would basically be about to here and then just as much that way. It's a big capacitor. So what is the capacitance of this parallel plate capacitor?
Are we assuming kappa is equal to 1?
Yes, we are.
So it would be 1 times that 8.85 times 10 to the negative 12 times 4 meters squared divided by 0.5 meters?
Divided by what?
0.05 meters.
Yep. All right, so first off, because of I gave you the physical characteristics of the capacitor first, and it's a parallel plate capacitor, using this formula is very convenient. So 1 times 8.85 times 10 to the negative 12 times 4 divided by 0.05.
That's 7.08 times 10, times 10 to the negative 10th.
Okay. Units.
You scoot over this way, or that way, sorry, I just need those. Are there units on the sigma or the 8.85 times 10?
Yes, there are. All right, so if we look at the units that way, units of this are coulomb squared per Newton meter squared,
Okay.
and the 4 is meter squared,
Yeah.
and the 0.05 is meters.
Meters. So coulombs per Newton meter. Is that right? The meter squared canceled out.
Yeah, you were close. Or did I miss it? Say it again.
Coulombs per Newton meter.
Yeah, you still missed the same word.
Okay. Coulombs per Newton per meter.
Yeah. I like the other way better. Squared.
Coulombs per square. Okay.
All right, so coulomb squared per Newton meter.
Gotcha.
Yeah, there's a simpler one.
Is it farads?
It is farads. A Newton meter is also a joule. So that would become a coulomb squared per joule. A joule per coulomb is a volt. So that becomes a coulomb per volt, which apparently is a farad.
Interesting.
It makes sense that ultimately you would break down into a unit of charge divided by a unit of voltage. Just recognize that this C and that C over there are not the same. This is a unit, that's a quantity or variable. All right, so we ended up with 7.08 times 10 to the negative 10 farads. So we actually, so that was 1, this is 4 meters squared, this is 0.05. Okay. What next? What can we find? I know capacitance. Oh. What's the voltage across the plates?
10 volts.
Yep. There's a gain 10 volts there, I'm gonna lose 10 volts going across there. It's gotta be 10 volts because it's the only thing in my circuit besides the battery, and the battery's setting that. So this is 10 volts. Now what can we find?
I guess we need to find Q first, since we need Q to find electric fields, right?
How do we find Q?
Capacitance times the voltage.
Yeah. Basically, this formula, again, this is for a parallel plate capacitor, and this is for any capacitor. So I know that my 7.08 times 10 to the negative 10th is equal to the charge divided by 10 volts. So we end up with 7.08 times 10 to the negative 9th units.
Coulombs.
All right, let's find the electric field from the coming from the plates. Or total, actually, we have 2 ways of solving for both of them. Just to end a possible difference in two answers.
So what's on top of the sigma and the plates and total formulas for the
Here?
electric? Yes. What is that sign? What is that?
Yes. Sigma.
Oh, that is sigma.
That
Okay.
is that's a lowercase sigma.
Okay. Then what's under it?
epsilon.
Oh, that's epsilon. Okay, I was getting sigma and epsilon. Okay, I was talking about, yeah, what's above the, okay, so that's sigma.
Yep. Fortunately, epsilon was kind of like an E, it starts
Right.
epsilon.
Okay.
And by the way, there's two different epsilons. There's that epsilon and then there's that epsilon. And that's just easier for me to write, but on paper, when you're using a word processor, I think that's the default one. So
Okay.
just be aware that they're both the same thing, just different fonts.
Gotcha.
All right, so anyway, was your
Sorry,
question answered or?
Yes, but then I just didn't, so I guess what is sigma?
What is sigma?
I don't know.
Charge density? Is it charge density?
More specifically, not just charge density, which one? There's three. Or if you just say charge density, there's sort of an implied volume, but this is not a volume one.
Right. Area,
Yep. Surface area. It's a surface charge
Surface area.
density.
Okay.
So sigma is the charge divided by the area. So we could throw sigma in there too, but. So how do we find electric field?
So we do Q divided by the area,
Okay,
which is, I guess I can do. Yes.
all right, so we got Q divided by the area, 7.08 times 10 to the negative 9th, divided by 4. All right, so we got a number.
1.77 times 10 to the negative 9th.
Units?
Coulombs per meter squared.
Yep. It doesn't simplify any more than that.
Okay.
All right, so we have the charge density now. Now what?
So now we need the total, or is that no? Oh, so now we do that divided by point. Which is 200.